Hi, I'm Theorem, and today I will be reviewing this paper. It's called Reformulation of the No-Free Lunch Theorem for Entangled Datasets. It was actually published really recently in Physics Review Letters, and I think it's an interesting paper, so hopefully you guys find it interesting. Okay, so for today's presentation, I will be talking about the classical no-free lunch theorem, and then I will move on to how they reformulated the quantum version of this theorem, and then talk about some of the quantum hardware and numerical experiments that they did to confirm this theorem, and then talk about some comments that I have about this paper. But first, I would like to introduce what the no-free lunch theorem is. In order to do this, we need to first think about the supervised machine learning setting. And I know that some of you are familiar with this, but I think that some of you might not be. So I would like to give a very gentle introduction. So let's say that there is an unknown function f, and in this case, let's say that this input and output x and y, they are discrete sets of size dx or dy. And let's say that we have some subset of x and y that's called S, and we call this the training set. And it's basically pairs of xj and yj, which are elements of x and y, except that this yj is actually f of xj. And let's say that we have a training set of size t. Then we can define a supervised machine learning task. So using this limited training set S, we try to train a hypothesis function hs that acts like f on all x that is in x. So using a limited training set, we try to create a function that is a good approximation of f. So we would like to ask, is there a learning algorithm that always gives an accurate hs? And it would be very nice if you had such an algorithm. But the problem is that actually there is no such algorithm. And in order to do this, we need to talk about the no-free lunch theorem. And there are many different ways of talking about the no-free lunch theorem, but I would like to talk about the formulation that they give in the paper. So in order to talk about how good hypothesis function is, we need to talk about the risk. So it's a value that can quantify how similar these two are. And we can define this in many ways, but in this paper, they define risk as follows. And it's a function that is dependent on f and hs, obviously. It can be written as some average over the probability of these two being different. And the no-free lunch theorem says that if we average over f and s, this risk value has some lower bound, as written as follows. So we can, since this may not be zero, then there will be some cases where the algorithm that we choose cannot create an HS that is very similar to F. So let's look at this inequality, and let's think about what this means. So if we just take it at face value, it means that averaged over all learning tasks, the risk has a lower bound. And remember that we can define a learning task with a training set and a target function. So this is basically averaging over all learning tasks. And this also means that no learning algorithm succeeds all learning tasks. So if this is non-zero, then there will be cases where this risk is larger than zero. And also one thing to notice is that this lower bound can be reduced if we increase t. So a large data set is an important resource in supervised machine learning. So we can ask, what happens to this bound when we use quantum computers? And that's what the authors tried to do in this paper. So note that the title of this paper is actually a reformulation of the quantum no-free lunch theorem. So that means that there was an original theorem, right? So I'd like to first introduce the original theorem, and then move on to how they changed the setting and created a reformulated theorem. So this is the original no free lunch theorem. This was from an arXiv paper published in that was first put onto arXiv in 2020. And they define their setting as follows. So let's say that there is an unknown unitary U. And of course, the input and output dimensions are the same. And we have some training set S. And instead of just some input and output, we have input and output states, where this phi j is the input state, and then psi j is the output state, which is exactly equal to U times phi j. And here we have a training set of size t. So we can define a learning task where we use S to train the hypothesis unitary V to act like U. And we can define a quantum version of the risk as follows. So we can think about the trace distance between the state that is created by U psi and V psi, and these should be similar. And we want to know the average of them, so we integrate over the states. And it turns out that if we average over all of the unitaries and all of the training sets, we have some value like this. So this is one version of the theorem. And then what the paper I'm trying to review suggests is that we change the setting a little bit. So likewise, we have some unitary that we don't know, and we want to know what this, how to represent this one. And we have a data set as follows, except that we can see that the input and the output has some, is part of some reference system. So instead of just the input and output, we have some reference system. And psi j is part of this Hilbert space X tensor product of the Hilbert space R. And phi j is likewise in this space, and it is also just U times psi j. So U just acts on the X Hilbert space. And likewise, we have a data set of size t. And there is one other condition. So all psi j has Schmidt rank R in the XR split. And just in case some of you aren't familiar with the Schmidt rank, what this means is that we can write all psi j as follows. So we can write it in this form. Here, psi I are, here the sigma I are non-zero coefficients, and ui and vi are orthonormal. So the rank R is here. So we can represent psi j in this form with R terms. And we can likewise think of a learning task where we use SQ to train the hypothesis unitary V SQ to act like U. And we define the risk as the same way as before. Actually, this trace distance is written here as dt. So it's the same definition as before, except that in this setting, we added extra reference system. And once we add this reference system and we have some assumption about the entanglement, we have some different lower bound as shown here. Are there any questions about the settings of the two theorems? I think everyone's clear, so I'll move on. Now let's take a look at this lower bound. So when R is 1, so when Schmidt rank is 1, then the average risk is non-zero when t is less than t. Can everyone agree with this statement? This is true. We need t to be very similar to d, but this d is increases exponentially with the number of qubits. So this means that we will need an exponentially increasing data set for training. But when R is D, then we only need t equals 1 data set for training. So we only need one pair of input and output to train an arbitrary unitary. And actually, when R is equal to 1, we can see that this bound is the same one as the original theorems, this bound. So the authors of this paper claim that entanglement is a resource in quantum machine learning, especially in the using quantum computers to train quantum data, then it is an important resource. And they did some experiments to show that this is actually true. So the first experiment that they did is learning a 1-qubit unitary on Rigetti hardware. So they follow these steps. First, we generate some random unitary U and some random training set SQ. And of course, we set the Schmidt rank of these states. And since we have a learning task, because we have a training set and target unitary, we can start training. So we train DSQ by minimizing this cost function. So this is just simply the fidelity between the input and output states, where the input state is acted upon by V. And then once this training is done, then we can calculate this value, because actually this value can be, there is some explicit form of this integration. And I'm not very familiar with the details about this calculation, but there is some paper that shows that this can be written as in this form. And so we can easily calculate or even measure this value. So we can calculate this RU. And then they repeated this for 10 random U and 10 random training sets. And then saw how the statistics changed for the Schmidt rank of the training sets. So just for some clarity, there I also inserted the images for the training circuits. So when we calculate this fidelity, we can use these circuits. When R is equal to 1, we don't need a reference system, so we can just use this circuit. And then if we have R is not equal to 1, then we need a reference system, and we can use this circuit. So the experimental setup itself is very simple. And the results are as follows. Okay, so there are four data points. The first one is when R is equal to 1, so it is not entangled. And then the second one is when we have R is equal to 2. And we saw the average risk, the relationship between the average risk and the number of training pairs. So we know that from the theorem that if we have a maximally entangled state, or basically with a maximum rank, then even with one data sample, we can train the unitary exactly. So we can see that here. And even for 2 samples, we can see that it actually learns the unitary quite accurately. But if we have unentangled inputs, then for one training pair, it is not enough. And we compared this, the authors of the paper compared this with some classical bounds. Actually, you might be curious about why there are 2 bounds for the classical case, since I only talked about 1 bound previously. So I left some details out. So I would like to explain that. So actually, there can be different lower bounds if we think about different f. So in the no free lunch theorem, we deal with this value. And so if we restrict f to some class of functions, then we can intuitively come to the conclusion that we will have different lower bounds. So since we're averaging over different sets of f, we can have different values for this. So actually, when f is just a matrix like this, depending on the class of matrix, there are different bounds, and I've written some here. So there's something called stochastic matrices, and I won't go into detail about the definitions, but depending on the type of matrices, we have different lower bounds. And one can think that, of course, unitary is one of them. And actually, if we draw unitary, it should be something like this, something larger than something outside of stochastic, but has some overlapping sides. So that's why we have different bounds here. Deterministic and stochastic, and deterministic and stochastic. So since we looked at some very simple example of 1 qubit, the author moved on to a more complex example where they tried to do learn an 8-qubit unitary using simulation. So it's quite difficult to do a learning task using actual hardware for this type of problem. So they try to do it with simulation. And let's look at the results. So likewise, we are looking at the average risk, the relationship between the average risk and the number of training pairs. And since we know about this bound, we know that this relation will be related to the Schmidt rank of the data samples that we use for training. So when R is 64, when R is maximized, we see that if even with one sample, we can achieve average risk of 0. And we can see that this that all of the, regardless of the value of R, if we have more training pairs, then on average the risk falls. But the speed at which it falls depends on the value of R. And we can also compare this with some classical bounds, but we can see that overall, if we have enough training pairs, then usually if we have R is larger than 1, then we have some better scaling than the classical bounds. And just to elaborate, this experiment was averaged over 10 random unitaries and 100 random training sets. So I would like to quickly go to the conclusion. So this paper claims that using entangled datasets, one can use non-exponentially scaling dataset for QQ learning. So when we are trying to use quantum machines to learn quantum data. And does this theorem guarantee scalability of QML? And I don't think so, and also the authors don't think so. Actually, in the end of the paper, they say that there are still many issues that needs to be discussed. One is Barron plateaus, and I know that I think Lee Ho-jun presented about this recently. And also one important thing I would like to touch on is that when I read this paper, I thought that maybe we can actually use this in some actual experiments. But the problem is that we need to prepare this entangled data set. If we look at the experiments that they did, they're trying to learn U, but they use U in their experiments. So I don't think that this is a very very good example. Of course, this is just for proof of concept. But if we're actually trying to use this for our research, then we will need some good way to prepare the data set. I think that may be a prohibitive cost to trying to use this, because in order to create this entangled data set, we need to increase the number of qubits. And of course, if we're trying to prepare some state with large amounts of qubits, then that will result in more cost. So yeah. So I don't think that this theorem guarantees scalability of QML, but if we can somehow prepare the entangled data set and we are doing QQ learning, then this theorem might be useful. And also it provides some insight into how entanglement can be used to improve the scaling of quantum machine learning. Thank you. I talk really fast, so if anyone has questions.
Thank you for the Thank you for the presentation. And I was wondering about the preparing data set. So when you mean by entangled data set, you mean state phi, not state psi.
So I think I mean both of them. So actually creating some states with large Schmidt rank is actually easy, right? We can do that arbitrarily, but the problem is we don't know this output state in that case. But I think that if we can make this easily, then this is hard, and if we make this easily, then this is hard, usually. Because we can't use U. If we fix this one, then it's difficult to know this one without knowing U. And when we know this one, it's difficult to know this one.
What I understand is that U is just some other physical condition when you want to run the condition.
Right, right.
So then why is difficult to apply U to state?
Um, I guess it's different depending on how we define the problem. But the way I thought of it was that we don't know what U is. So I guess we know how U acts on some states, but we don't know how U acts on everything. And we don't have access to U. That's the setting I was thinking. Oh, yes, but that's true. But so when we actually try to use this one, let's say that we actually try to use this in our research, like right now, then what we will have is like this setting, right? So we have just input states and output states with no reference system. And then, okay, so yeah, thank you for the clarifying question. I think that this is more accurate. And what I was trying to say is that if we try to use this, if we try to take advantage of this theorem right now, then we will be given this type of training set. And we want to make this type of training set with that training set. And I think that is difficult.
Except given that actually we just how if you want to create the data set, we just choose random input state, which is psi.
Okay.
Then apply it to the system. Then we get phi.
Okay, so the thing is, oh yeah, sorry.
It's not that difficult.
So what I was thinking about a problem where you can't just apply it to U. So if you can just use U, then why do you need to learn U? Is my thought. Other given states? Here?
Like, yeah,
Or-
like not for this scenario, but
Yeah.
like in general.
In general, that kind of depends on your problem setting, right? But like usually from like what we usually do is for when let's say we're trying to use some QNN, then we have some encoding circuit where we put in some classical parameters, and that results in some states. So we can efficiently prepare these states in this register. But I think that if we try to create some large entangled states, that includes some reference, then that's kind of difficult. You will need to make many like controlled integers, and that will be very large. Then if we don't have access to U, and I think that in most cases we won't have access to U, because if we can use U, then we don't need to learn a representation of it usually. So unless we're trying to do maybe like eigenvalue decomposition of U, if we're not trying to do something like that, then I think that we don't need to learn U when we have U. So I was thinking about a setting where we don't have U. So even making this one, if we have access to some efficient circuits that create the data on the X Hilbert space, even if you have that, then it's difficult to make this one and also this one. I think I kind of rambled on, but hopefully my point was.
Reference system, like would be
I think that we can assume that, right? We were thinking, so I was talking about a setting where we have some QQ learning task, and we're trying to exploit this theorem. In that case, we can usually efficiently prepare the input states and the output states, but even with that, it might be difficult to create these things.
actually, I'm not sure. Like, I presented about power of data and
Oh, yeah, yeah.
like, is that paper like related with this one?
Oh, sorry, I need to kind of think back on the paper. I don't think that paper, I don't think the main point of that paper was about the size of the training set. Rather, it was that if we use quantum kernels, we can find cases where for certain data sets, like the I don't know what is the correct mathematical word, but if we create a feature map to the Hilbert space, then the way that the data points are mapped can be quite different to some classical feature map that we mostly use. I think that was the main point of that paper.
Yeah.
Oh, right.
I'm not sure if I get it.
That's similar, but I think
Here also, just if you have like, I understand it correctly, if you
right. I think here they talk about the size of the training set on average that is needed to achieve a certain
certain
risk, right?
Okay.
But the paper that you mentioned, the one about power of quantum data set and power of data in quantum machine learning, right? That's the title of the paper. I think that one is about the feature mapping itself and how that can be different, very different from the ones that we use classically. So the original one was without the reference system, and then we just have this one, and then so let's say we want to make this 0, then we need t to be basically d, right? Actually, it needs to be square root of d squared minus 1, but I guess that's basically the same if d is large, right? So we need t to be d, and d increases exponentially with the number of qubits. So we need exponentially many training samples if the qubit increases. I think that's the message of this one. It doesn't have to be, but so from what I remember, the maximum of the Schmidt rank is the minimum of the x dimension and r dimension, right? So if we want to make a large Schmidt rank R, then we need a large reference system, I think.
The dimensional reference system doesn't have to be large.
It has to be large if R is large.
Larger than the dimensional system, but it doesn't have to be larger than the dimension.
Yeah. It depends on how large of a Schmidt rank you want to make. So even if you want to make the largest R, then the dimension of reference system should be about the same as should be the same as
We have a larger reference, then we may have if we have a better entanglement, then you don't need or training set. That was my initial.
But actually, like the way I think about this theorem is that if we want to learn if we want to specify unitary, we only need to know how it acts on all the bases, right? So we just need that many input states, and that's basically determined by how many UI we have, right? Because these are all orthonormal. So these are basically the basis states that we are inputting to U to see how it works. So even if we increase R, then that shouldn't help too much, right? Other than just indirectly helping with the number of UI we can put into our one sample. Okay. So usually we think about when we are trying to learn, if you have let's say some parameterized gates, and we want these parameterized gates to be U. So we basically think about that type of situation. And usually how we do that is we make input and output states. And these input and output states are states of the input and output of U, right? Usually. But they think about adding some reference system. Some like, you can think of like maybe ancilla qubits or some additional qubits, other than just the qubits that U acts on. So we increase the number of qubits, and then we have some input, and then we have some output. And this output is simply U acting on X and some just identity on the reference. There's no more questions. I'd like to end this meeting. Thank you.